Hello everyone. This series is a summary of power system operation and planning. Today I'd like to talk about forming and solving power flow equations. We use these equations a lot, active power P and reactive power Q injection at node I. But there's no need to memorize anything. Just start with calculating the complex power S at node I and do the following steps. Let's start with S equals to UI conjugate. II is the current injection at node I and can be written in the form of this summation. Yj is the admittance between node I and node J. Now we write them in polar coordinate form, amplitude U and angle delta. The admittance Yj can be written as conjugate G plus J susceptance B, and since there's a conjugate, there's a minus sign. Uj also in polar coordinates. Delta Ij means delta I minus delta J. Then we apply Euler's formula, rearrange them, put the real part together, put the imaginary part together, and finally we get the formulation of P and Q injection at node I. When we solve the power flow problem, if we have n nodes, then we have two n equations, P and Q for each node. For each node, there are two unknown variables, so there are two n variables in total, which is exactly the number of equations, so this is solvable. Let's look into the details further. We have three types of nodes. PQ node, where P and Q are known, but voltage, amplitude, and angle are unknown. PV node, P and V known, Q and delta are known. If we have a slack node to balance power, we'll talk about that later. And its P and Q are unknown, and V and delta are known. This is the number of each type of nodes. Now we introduce the concept of explicit equations and implicit equations. The simplest way to distinguish them is to see if the power injection in the left-hand side is known. If so, then it's an implicit equation. If not, then it's an explicit equation. If we substitute known values in an implicit equation, then we still need to solve the equation to get the unknown values. But if we put known values in an explicit equation, then the unknown values in the left-hand side are directly computed. For example, for PQ nodes, if we know P and Q and put the values in the equation, we still can't get U and delta immediately, so these two equations are implicit equations. And it's the same for the P equation in PV nodes. However, for the Q equation in the PV node, if we put the value V and delta, which can be calculated from the implicit P equation, then we simply calculate the right-hand side and the Q value is obtained. P and Q equations in the slack node are also explicit equations. We just need to solve the implicit equations where injection P and Q are known to get U and delta values. Then substitute these values into explicit equations. Why do we need a slack bus? Because we need to balance power flow, or say to account for power loss. The choice for a slack bus can be arbitrary. Note, it is different from the reference node, which provides a reference voltage for all other nodes and is usually the ground. For simplicity, we can make the slack node the same node as a reference node. In practice, we can make it distributed slack nodes rather than one single slack node to reduce further transmission of losses. There is a simple two-node network application here. First, substitute values into P1, P2, Q1, Q2 equations. The power injection at node I is equal to power generation minus demand at that node. So for node 1, that is P1 generation minus 0, and for node 2, P2 is equal to 0 minus P2 demand. If we want to calculate active power loss, just add all the active power at every node. We can prove that it is non-negative. Just add P1 and P2, and it is bigger than this, which can be written in the matrix form. We can check the eigenvalues of this matrix Q. It is positive semi-definite, so it's proved. But are the power flow equations always solvable? Let's explore power flow feasibility. Still look at the two-node example. Let's use the formulation we just conducted, but with the assumption that G and B are equal to 0. G can be neglected when the line resistance R is a lot less than X in transmission networks. And in short transmission lines, load capacitance dominates and shunt capacitance can be neglected. Now, to eliminate sine and cosine, we square both sides and add them up. Let's convert it to a quadratic function of u2 squared. To have real value solutions, delta should be non-negative. We make some calculation here, and now it's a relationship between P2 and Q2. So the power flow solution is feasible in this area. How do we enlarge the feasible region? We can either increase U1 or increase the susceptance B, that is to decrease line impedance by adding series compensation or adding parallel lines. Or we just add local reactive power sources at node 2. If we fix the Q value and draw the V and P relationship, we get a nose curve. This point corresponds to an infinite derivative and is called voltage clefts. Jacobian matrix will also be non-singular here. You can see a P value corresponds to an upper branch and a lower branch voltage. And the system should run at the upper branch voltage because node voltage should be near 1, and then there is less loss in transmission and thus it is more efficient and economical. Let's talk a little more about line capacitance and shunt capacitance. Line capacitance models are different for different lengths of transmission lines. As we just said, in short transmission lines, line capacitance can be neglected. For medium-length lines, line capacitance is like this. For long lines, line capacitance can be regarded as uniformly distributed along the lines. For cables, even short cables have ineligible capacitance. And why do we use shunt capacitance? If the load at the receiving node is low, then the voltage at the receiving node may be larger than that at the sending node. This is called Ferentin effect. In such cases, shunt inductive compensation is needed. But in more general cases, there is a lagging power factor due to inductive loads such as induction machines. And shunt capacitors are needed to supply reactive power, boost voltage magnitude, and improve power factor. By leading or lagging, we mean how currents and voltage angles are. For example, according to physical laws, voltages of inductive devices are proportional to derivatives of currents, so V is proportional to omega Ji, which means currents lags voltage in the phasor plane. Another thing to notice is that although we often mention QV coupling and PF coupling, it doesn't mean that P and V or Q and F are isolated. We do find that low active power loads leads to a voltage boost due to line capacitance. It is just in steady-state analysis near a stable frequency that we can use phasor expression, and then we can do PF or QV control separately. Thank you for watching, and I'll talk about power flow solutions in the next video.